Hello and welcome back to Paleocast. I'm Dave Marshall.
And I'm Liz Martin.
And in this episode, Liz will be talking to Dr. Richard Butler from the University of Birmingham. But before we get to details, Liz, where are you?
I'm currently in Japan.
Why are you in Japan?
That is a good question. So I'm writing up my thesis while my husband is doing a research project here. So I'm just along for the ride and finishing my thesis while being isolated from everyone.
Nice. And give us a very concise, precise explanation of what your husband's doing.
Physics. That's complicated. Yeah, he's doing an experiment with a company here. So
you've just gone to write up in isolation.
Pretty much.
Away from all distractions.
Yeah. I mean, there's plenty of distractions, but they're different.
That was going to be my next question. Have you been distracted by what Japan has to offer?
A little bit. Fortunately, where we're staying, there's not a whole lot, but you can easily get into, we're about a half-hour train ride from Tokyo, so it's easy to go in and get distracted for a long time there. But basically nobody speaks English, so it's pretty easy to just stay completely isolated and in my little box apartment.
Well, good luck with writing up. And are you going to be doing any kind of paleontological stuff while you're there? Are you going to see any specimens or go to any museums?
Yeah, I'm going to do a little bit. So there's the National Science Museum has actually a really nice pterosaur, which is from Brazil. But it's one of the best in the world. So I'm going to go and take a look at that at some point. And there's also a museum where all of the dinosaur fossils from Japan actually come from. They have an area called Fukui, which is where a whole bunch of dinosaurs have been found. So I'm hoping to go down there and check out the museum at some point. But it's a little bit far from here, so we'll see.
Well, it might be worth an episode in the future then.
Yeah, maybe. I have no idea who I would talk to.
So if you fancy this as an episode or if you have any recommendations, we're always open to them, so please write in. Right, so now I think it's time that we covered our usual admin, and we should say that we finally got our website back online now, so sorry about the absence. It seems like everything that could go wrong with fixing it has gone wrong, but we're all sorted out now. Ironically, one of the problems with it was that the security software that we installed on it had a vulnerability, and that is what got hacked.
Jeez.
Yes.
That's annoying.
Yeah, so it took us a while to figure that one out, but we're there now. We got a clean bill of health, and it should all be online. And with that out of the way, what's this interview actually about, Liz?
So this is an interview that I actually did at SVP last year, talking to Richard about some of the work he's been doing on kind of early Archosaur radiation and the evolution of sort of bird-line Archosaurs. So leading up to dinosaurs and sort of the early Triassic, middle Triassic evolution of those sorts of animals.
And so if you recorded it last year, why has it taken us so long to release this interview?
That would be because it's partially on a new paper that Richard has coming out on Wednesday, which will be, I guess, today by the time this episode comes out. So a new paper in Nature, which is on a new species that they've described. So Sterling Nesbitt, Richard, and a whole bunch of other people on this new specimen from the Middle Triassic. And it's kind of exciting looking at this time period and this area of evolution that we don't know a whole lot about. So that's why we've had to wait a little bit on this episode until he could actually talk about the specimen in question.
And we've got pictures of it, yes?
Yes, yeah, we've got a couple of pictures from the paper and also some reconstructions. And then we also talk about some of the other stuff Richard has done on other important fossils of that kind of age and evolutionary history. And those are all on the website as well.
So make sure you check those pictures out on our website, and also if you enjoy this episode, please share it on social media as it really helps out. Thanks to everyone who's been rating us on Facebook. We've had a few 5-star reviews, and it'd be nice to get some more on iTunes as well.
We hope you enjoy this episode.
Okay, so I'm at the Society of Vertebrate Paleontology annual meeting in Salt Lake City, and I've sat down with Dr. Richard Butler from the University of Birmingham. So thanks for joining me, Richard. It's really great.
Thank you for the invitation.
So can you start off by telling me a bit about yourself, how you got in Birmingham?
Yeah, so I'm from the UK originally, and I was an undergraduate student at Bristol studying geology, and then did a PhD at the University of Cambridge, which was on early dinosaur evolution. So I specialised in ornithischian dinosaurs. And then I was postdoc for seven years in total. So I was at the Natural History Museum in London for 3 years, working on various projects, including dinosaur plant co-evolution. And then I spent 4 years in Germany at the University of Munich and the Bavarian State Collection for Paleontology. And at that point I got interested in kind of Permian and Triassic reptile evolution. And then I got a permanent position in Birmingham in 2013, so that's where I've been since. And I have a research group there who are focused on late Paleozoic and Mesozoic vertebrates, particularly reptile kind of anatomy and diversity, and also looking at broader scale kind of patterns of tetrapod evolution and diversity on land through the Phanerozoic.
Today we're going to talk a little bit about some of the work you've done on early Archosaurs and Archosaur evolution. So can you start off by telling us kind of what are Archosaurs and Archosauromorphs and the difference between those groups?
So Archosaurs are a major group of vertebrates that include birds and crocodilians, so two important living groups of vertebrates. They also include the common ancestor of birds and crocodiles and all of the descendants of that common ancestor. So that includes pterosaurs, flying reptiles, it includes dinosaurs, and it includes various animals that lie along the lineage leading towards crocodilians as well. Archosauromorphs is a broader group that includes archosaurs, but also all of the other reptiles that are more closely related to them than they are to lizards and snakes, to lepidosaurs. So there are a bunch of groups of extinct Archosauromorphs that fall outside of Archosauria that are around during the Permian and the Triassic, and they include some really weird animals. So there are, for example, these very strange, very long-necked aquatic tanystrophiids. There are these important Triassic pig-like herbivores called the rhynchosaurs. And there are these rather Komodo-like, dragon-like, big-headed apex predators called rhiphroseuchids.
When did the first proper Archosaurs appear?
So the very earliest Archosaurs appear during at the end of the early Triassic, so about 247, 248 million years ago. So not very long after the Permo-Triassic mass extinction, which happens at about 252 million years ago, and which is the most important, or the largest mass extinction in the history of life on Earth. Archosauromorphs actually appear a bit earlier, so we have Archosauromorphs in the Permian, so a few million years prior to that mass extinction.
And was it that Permo-Triassic extinction that kind of allowed Archosaurs to diversify?
Possibly. So we see a major change in global vertebrate faunas after that extinction. So before the extinction, basically ecosystems are dominated on land by synapsids, so by groups that lie along the mammalian lineage. And afterwards, so they take a big hit at the Permo-Triassic extinction. And through the Triassic, we basically see this kind of transition where synapsid-dominated faunas are replaced by Archosaur-dominated faunas and by Archosauromorph-dominated faunas. And of course, that ultimately leads to dinosaurs and pterosaurs and crocodilians becoming very important from the late Triassic onwards.
And what features distinguish an Archosaur? What's kind of the typical, how do you tell if it's an Archosaur versus something else?
So Archosaurs classically were identified on the basis of some openings in the skull, one called the antorbital fenestra, which lies just anterior, just in front of the eye socket, as well as one in the lower jaw called the external mandibular fenestra. Actually, we now recognise that these are probably characters that distinguish a broader group of Archosauromorphs, which we refer to as Archosauriforms. So the characters that actually define Archosaurs themselves are still very much debated, but there are some features such as the extension, this antorbital fossa in front of the eye becomes larger and more extensive in the crown group.
And a lot of the work that you've done in recent years is focused on kind of early Triassic Archosaurs. Can you talk a little bit about the significance of that time period and why that's really interesting?
Yeah, so I guess the reason that the early Triassic is particularly interesting is that it follows immediately after this huge catastrophic extinction that we have at 252 million years ago at the end of the Permian. We have this massive flood volcanism in Siberia, and this leads to dramatic climate changes, largest extinction in the history of life. Synapsids take this, which the mammalian ancestors take this massive hit during this extinction event. And then we see, through the early Triassic, we see kind of the recovery of global ecosystems. So global ecosystems start to build up again. And groups that were previously marginal components of ecosystems diversify and become important, and they go on to dominate the Mesozoic world, so throughout the rest of the Triassic and the Jurassic and the Cretaceous. So it's really kind of the birth of the Mesozoic world that we're seeing in the early Triassic, so that's why it's a fascinating interval to work in.
Is it particularly easy to find fossils in the early Triassic? What's the kind of preservation like?
It depends which part of the early Triassic you're in. Immediately after the mass extinction, there are quite rich fossil deposits from places like South Africa.
Okay.
So there's a very good section across the Permo-Triassic boundary in South Africa. There's also good material from Russia. We've done fieldwork in recent years in India, and again they have quite rich deposits immediately after the Permo-Triassic mass extinction. Okay. But then as you go later into the early Triassic, there are very few fossiliferous deposits, and so it's actually, and that's actually the time interval when we would expect to find the earliest Archosaurs. So we only have a few fragments or a few specimens of early Archosaurs from that time interval.
Okay. What is the significance of the Manda beds in Tanzania, where I know you've done quite a bit of work?
Yeah, so the Manda beds are slightly younger in age, so they are at the beginning, probably, of the Middle Triassic. Okay. So somewhere around about 245 million years. But still pretty soon after this mass extinction, within 5 to 10 million years after the mass extinction.
Okay.
And they've been, they're a very fossiliferous set of rock units in southwestern Tanzania. And they've been worked by paleontologists since the 1930s. So there's a lot of material that was collected in the 1930s that is now in the Natural History Museum in London. And in recent years, my collaborator Sterling Nesbitt and a whole team of other people from the United States and from South Africa and various other places have been working there collecting new material. And it's a really important assemblage that we find within the Manda beds because it includes a lot of different taxa of early Archosaurs and Archosauromorphs, and a lot of those are very well preserved, so we have really good material of them. So it's really our kind of our first insight into this very important Archosaur radiation, our kind of a first snapshot of a lot of taxa from this radiation.
Okay. Is there anywhere else in the world that you can get similarly aged fossils?
There are other places, but there's nowhere as rich.
Okay.
So there are equivalent units in Russia and India and various other places, but they don't have the same kind of wealth of species that the Manda beds have, and the preservation generally isn't as good either.
What kind of species number are we talking about when you say it's rich?
So from the Archosaurs, we're probably looking at maybe around 10 species that we know of now.
Okay.
Which, keeping in mind that we're right at the base of the radiation, is a significant number. Now, it might be that there's more than one assemblage within the Manda bed, so some of those are slightly older, so they're not all directly contemporaneous. But still, it's providing us with a very significant snapshot. And those taxa, some of them are extremely significant. So, for example, there is a taxon called Nyasasaurus, which has been suggested to be possibly the oldest dinosaur. It's quite controversial, but possibly. There's also an animal called a Silasaurus. I can never remember how you pronounce it, which Sterling Nesbitt found. And this is a Silosaurid, so it's a member of a group of reptiles very closely related to dinosaurs. And again, it's the earliest member of that group. And actually, at this meeting, Sterling and myself have been presenting another new taxon that's hopefully be published in the next couple of months, which has actually been found. Material was first found in the 1930s and was never studied, or it was studied in a PhD but never published.
Okay.
And this seems to be the oldest bird-line Archosaur, so the oldest member of the lineage that eventually leads to birds. So this is a very significant new taxon that hopefully will be out probably towards the end of this year or early next year.
Okay. So in terms of kind of significance for dinosaurs, there's obviously Nyasasaurus, which might be the earliest dinosaur. Are there other fossils that look like they're, very close to dinosaurs other than this one that you're soon describing?
Yeah, so there are three taxa that are either dinosaurs or very closely related. So Nyasasaurus, if it's not a dinosaur, is something very closely related to dinosaurs. Then there's Silasaurus, which is this Silosaurid, so a member of herbivorous reptiles that are very closely related to dinosaurs. They're probably the sister taxon to dinosaurs.
Okay.
And then we have this new taxon, which is possibly the oldest bird-line Archosaur. So all of those are actually pretty closely related to the origin of dinosaurs, and they're really starting to show us how kind of dinosaur characteristics build up through the Middle Triassic.
Do you see in any of the other areas in the world where you have a similar time but isn't as rich, are there similar kind of animals and other things that look like they're on the way towards bird-line Archosaurs? This new taxon, I can tell you its name, I think, because it was actually given a name, and it's been in a PhD in the 1950s, and that name has been used in the literature. So it's known as Teleocrater. So this is a new taxon that we're actually finally going to formally describe. It seems to be very similar to taxa that have been known, have been described in the past from Russia and from India. Okay.
And it seems that these taxa form a clade of early bird-line Archosaurs.
Okay.
So it's also helping us to kind of, these are animals that were described, but they were very kind of enigmatic. People didn't really know where they fitted into the evolutionary tree of Archosaurs. And what we're now able to recognise is there is this group of early bird-line Archosaurs that's occurring in Tanzania right at the beginning of the Middle Triassic.
And how do these kind of studies contrast to previous finds or ideas about kind of the evolution of Archosaurs or that thing?
So they're giving us some really interesting new insights into particularly the origins of bird-line Archosaurs, so the lineage that leads to dinosaurs and ultimately to birds as the descendants of dinosaurs. So for example, we're seeing that the earliest members of that lineage were significantly larger than we would have thought. So we've always thought that the earliest bird-line Archosaurs were very small, maybe animals 50 centimetres or less in length, whereas these new taxa are probably up to a couple of metres in length. So they're not huge, but they're significantly larger than we've pictured historically the early bird-line Archosaurs to be. We're also learning more about kind of character evolution. So for example, one of the things that the Triassic paleontologists who work on Archosaurs are very interested in is how ankles evolve, because dinosaurs have a very distinctive way of walking that distinguishes them classically from other groups of reptiles. They have an upright posture where their limbs are tucked underneath the body, and this has a particular kind of ankle joint associated with it. And that's very different from the ankle joint we see in crocodiles, for example, which have an ankle joint that allows rotation between the two bones because the limbs are splayed out to the side of the body. And what we're seeing with these new discoveries is that the earliest bird-line Archosaurs, so the earliest members of the lineage that leads to dinosaurs, still had this crocodile-like ankle.
Okay.
And we can now see how that is reduced through time in that lineage.
Okay. Just thinking about how the idea of size, and we previously thought they would be a lot smaller, is that coming from sort of the finds that you get in Argentina? Because those are the early dinosaurs that are quite small.
Yeah, so the classic kind of model for what our immediate dinosaur ancestors look like have been animals that were first discovered in Argentina called things like Marasuchus and Lagurpaton, which are very small, bipedal, cursorial, so fast-running animals. Less than 50 centimetres in length. And what we're seeing actually is that there's a whole range of new discoveries that are showing that actually some of the closest relatives of dinosaurs were significantly larger. They were quadrupedal in some cases. They weren't necessarily fast running. Some of these groups were actually herbivorous, and we've always again thought of the dinosaurs as being primitively carnivorous. So we haven't figured all of this out yet, but it's opening up. I think we need to reevaluate kind of our classic ideas about what the ancestors of dinosaurs looked like and what the first dinosaurs would have looked like.
In any of these early taxa from the manda beds, do you have skull material? Can you tell whether it was herbivorous or carnivorous?
There's a number that have skull material, we do have some material for skull material for this new taxon, Teleocrater, that we're describing, and it seems to have been a carnivore. So,
okay.
But there are this other group of Silasaurids, which are very closely related to dinosaurs. The oldest member of this group, Silasaurus, is known from the manda beds, and this seems to have been a herbivorous group of animals.
So it seems to be a bit of something like carnivory and then herbivory.
I think the key picture is that this group of animals that are immediately kind of ancestral to dinosaurs are actually much more ecologically diverse than we realised previously. So we had this kind of relatively constrained picture of what they looked like. We didn't know many taxa, and as we discovered a lot more taxa over the last 10, 15 years, we've realised actually there's a lot more ecological diversity there than we previously thought.
And some of the new work that you've been doing includes some kind of interesting biogeographical work as well. Can you talk a little bit about that and trends you've found and how that relates to the manda beds and what you're finding in the Triassic?
Yeah, so one of the things we're interested in is, so if I step back a second and talk about the Triassic world, so the Triassic is a time at which all of the continents are joined into a single landmass, which we call Pangaea. So we have a single supercontinent, Pangaea, which has very strong seasonal variations in climate. And it's interesting biogeographically because you would expect, perhaps your default assumption might be that if you've got a supercontinent, it's going to be very easy for animals to move from one part of that continent to another. So there should be low barriers for dispersal of animals from one area to another. But that's the kind of the counter argument to that is that there is this strong latitudinal variation in climate due to the fact that we have a very this landmass creates a very strong seasonal variation in climate. And so one of the things we're interested in is understanding kind of what the distribution of major groups of Archosaurs and other tetrapods are on this supercontinent, and how the mass extinctions that we see both at the end of the Permian and at the end of the Triassic affect those. So we've been developing a new method, or a modification of an existing method, which is called phylogenetic network biogeography. So a network biogeography, basically, you identify a number of geographic areas, and those are kind of nodes within a network, and then taxa that are present in each of those geographic areas are links between those areas. So if you have a taxon that's present in two areas, that creates a link between those two areas. And you can basically kind of quantify the proportion of links that are present, so the number of taxa that are shared between areas, as a proportion of the number of possible links. So that the maximum number of links if taxa were present in every single area. And that tells you basically how well connected different parts of the supercontinent are, so how globally cosmopolitan the fauna is, as opposed to being endemic. Now this was an approach that was developed a few years back, and it didn't incorporate phylogeny. So one of the things we've been working on is incorporating evolutionary relationships, so that we're not only looking at whether a taxon is present in two areas, but also how closely related it is to taxa that are present in other areas. So we can incorporate more data using phylogenetic information. So we've been developing this method, and we've been applying it to all terrestrial tetrapods from the late Permian through to the early Jurassic. And basically what we see is that the mass extinctions that we see at the end of the Permian and the end of the Triassic cause large spikes in connectedness. So this means that after these extinctions, we have much more cosmopolitan global faunas. And then as we move away from those extinctions, so as you move into the Triassic, faunas gradually become more and more endemic. And what this seems to fit very well with this idea that mass extinctions are followed by what we call disaster faunas. So you have an extinction, wipes out lots of taxa, and then a few survivors basically become very abundant and spread out over the supercontinent, and are successful for perhaps a relatively short period of time. And then, so you have a very kind of globally cosmopolitan fauna, and then over time that kind of decays, and you start to get more and more endemism as differences between different geographic regions develop. So I think we've been able to actually quantify that pattern and show that it is definitely true for this time interval for the first time.
And that's consistent between all the groups you've looked at?
So we haven't really, we've been looking at across all tetrapods, so we haven't necessarily at this stage broken it up to look at individual clades. What we have done is looked at which groups are driving this pattern, and it seems to be largely groups that originate either just after the mass extinction or around about or just before the mass extinction. So it seems to be relatively new groups of animals that are surviving or originating immediately after the mass extinction, then become very cosmopolitan. So again, this fits with this idea of disaster taxa.
Yeah, that's really interesting.
So that's work we're so my postdoc David Butler was presenting that here on Wednesday, and it's work we're writing up at the moment. So hopefully out again early next year.
A lot of the other work that your group is doing is on kind of general diversity patterns in groups other than Archosaurs as well. Can you talk just briefly about some of the other work your group is doing?
Yeah, so the big project that we're engaged in at the moment is we've got some funding from the European Research Council to basically look at the big pattern of terrestrial tetrapod diversity through the whole Phanerozoic, so from the Carboniferous through to the present day.
Okay.
And this is something that people have looked at before, and they've suggested that actually the overall pattern is an exponential increase. So diversity just continues increasing and increasing more rapidly towards the present, with the implication that diversity is basically much higher today than it has been at any point in the geological past, and that there really haven't been any kind of constraints to hold back or stop that diversification. Now, there's a problem with this in that we know that the fossil record generally gets better as we go towards the present, and previous studies haven't really been able to kind of to deal with that fact, to try and kind of remove that influence of better sampling towards the present day. So that's what we're trying to do. We're basically trying to test that pattern and see if, when you take sampling into account, do you still get this kind of continuous rise in diversity through time, or is it something different? So an alternative is that maybe you reach some kind of diversity plateau or equilibrium at some point in the past, maybe as early as the Mesozoic, and then diversity is either constant or relatively slowly increasing since then. So that's pretty important implications for understanding the way that kind of modern ecosystems work. So it's actually a very kind of central question in current and a central debate in current evolutionary biology, whether ecosystems in the modern world are kind of constrained, or whether there is no kind of constraints on diversity.
Obviously, this is quite different from sort of traditional paleontology studies. So what kind of data do you use and analyses do you use to sort that out?
Yeah, so it's this is a kind of a meta-analytical type work, really. So it's we're basically collecting information on the geographic and stratigraphic range of species from the literature, and we're entering those into the paleobiology database. So this large online database that is attempting to summarize the fossil record. There's a huge amount of data in there already, some of which has been entered by our group in the past. But it's missing data for terrestrial tetrapods in some key areas, particularly the Paleozoic and parts of the Cenozoic. So we're really kind of focusing on trying to fill in those gaps, and then we'll have a complete data set that we'll be able to use to estimate diversity patterns through time.
Okay. What do you think is kind of the next big area? I guess you're working obviously on part of it, but is there something else that you think we really need to focus on in the future? Just to be annoying and ask a hard question.
So I guess one of the things that I'm really interested in, and one of the things where I think paleontology can yield can really help with understanding the modern world is understanding how kind of ecosystems evolve through time, and whether there are changes in the nature of ecosystems. Do ecosystems, for example, become more resilient to environmental change through time, as they become essentially more mature? So this is actually something that we're hoping to work on in the future. We're waiting on some news about whether we're going to get some funding to do that or not at the moment. But I think that that's one example of where paleontology can actually yield useful data for understanding the modern world, and potentially for helping with kind of conservation efforts and so on.
That's very interesting. Well, thank you very much, Richard.
Okay, thank you very much.
Paleocast was brought to you by Dave Marshall, with Joe Keating, Laura Soul, Liz Martin Silverstone and Caitlin Colery. It It was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on contributions from you, the listeners. If you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. We'd also like to thank the Ocean Collective for use of their music. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programmes. Subscribe to our Twitter feed @Paleocast and like us at facebook.com/Paleocast to get all the latest news.